This is an actual recording of an estimate on a Pioneer receiver. I told Gary, our longtime customer, that he would see the whole estimate process on this. He brought this in, and he says there's an imbalance in the channels, and it may occur intermittently, and it may occur on all modes. So what we're going to do, and Gary, I think you're familiar with our test equipment here, but just to refresh your memory, we're going to play a steady state signal from a laboratory generator into the auxiliary inputs, and we're going to be able to view the left channel on the upper display on the oscilloscope, and the right channel will be on a lower display. And what's going to be more valuable in this case, because we actually want to get a quantitative decibel reading, is those two orange dots are the beginning of a horizontal bar graph. The upper graph bar will be the left channel, just like on the scope, and the lower will be the right channel, just like on the scope. So I don't know how we can do this nicely here. Zoom out a little bit. And let's turn on this beautiful machine, see what we find. Oh my God, aren't they magnificent? Okay. Okay, so right off the bat, I can hear scratchiness in the volume control, which I think you also mentioned you may have had. So while we're on the subject here, let's see how well this volume control tracks. What I'm going to have to do is go to a dummy load as we get increase in volume. So by tracking, I mean as we turn the volume control, the left and the right bars should be equal within a decibel or two. Right now, the right bar is maybe 2 decibels below the left bar. Still certainly acceptable. And let's see how this tracks throughout the whole range. I need to shift gears here. Well, we're still about 2, maybe we're 3 decibel difference now. And I'm going to go to the dummy load because you're not going to be able to hear me. And we're going to keep increasing this. As we're increasing the volume, the difference in tracking is less. We're now approaching ear-splitting volume, and both left and right channels are almost equal. Okay, but that's pretty good. So now we're going to go back to a lower volume level, which it's easier to see if there's a channel imbalance. Now I'm going to exercise some of the switches and controls. The most egregious switches on these items are the tape monitor switches. We're going to take a look at them all, but I want to see where the tape monitor switches are. That's why I had to turn the light on. Okay, so now that's the tape monitor switch, and same result every time. There's another tape monitor switch, and of course we have a phone call. So I'm going to put this in pause for a second. Okay, we're back, but he says he's going to call back shortly, so we'll be interrupted again. So if I remember correctly, we're going through some of these switches and controls. There's 2 tape monitor switches, so I'm now on monitor 2, and we're still getting the same, we'll call it a negative result, because it's not failing. The positive result would be failure. Let's go to the adapter. Nope. Maybe it's increased a little bit, but certainly not what I want to see. I want to see 10, 20 dB difference. No, no change. Let's, what else do we have here? Mode, stereo, mono. It's changing by a decibel. That would not be an audible change. This is loudness. No. Still a 2 decibel difference. Not going to happen. Let's go to the muting switch here on the far right. Muting gives us 20 dBs, which is what we're seeing. Well, still the same. Let's just lean on the auxiliary switch. We're going to check some of the other functions too, but just lean on this. There goes the phone. I'm going to put this in pause. And the phones just keep on ringing. Okay, we're back. And what were we doing here? Don't know what we were doing. Oh yeah, we're just going to try some of these other function controls. We're actually going to test for an imbalance in FM also. Not happening, and I'm just going alternating between the phono and back to auxiliary. Not happening. Not happening. This is AM. Not happening. What else do we have for controls here? We have low and high filters. Slight change, but really nothing that would be noticeable to the human ear. What else do we have over here? No. Still the same 2 dB difference. So right now I am seeing no audible difference in the channels. No, those are the tone controls, bass and treble, nothing. Balance. We have it at the center detent. We're going to keep returning it to the center detent. And still no big real world difference. All right. So right now, none of the switches and controls are exhibiting the problem. There's other items inside, for instance, the speaker relay that can exhibit that problem. So I'm going to tap on this. Actually, it's a bit more than a tap. But nothing's happening. 0. We're going to open and close the speaker relay a few times and see if changing the contacts will make a difference. Okay, so let's turn it off. And these items typically employ between 5 and 10 second turn on delay. So we're going to turn it back on. Wait our 5 to 10 seconds and see what occurs. Nope, same. 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 We're not coming up with anything fruition-wise as far as channel imbalance. See, a channel imbalance would be this. That would be audible. This is not audible. That's audible. This is not audible. Let's go to FM. And I'm going to turn the speakers back on so I can get an idea of what's going on here. And we're going to go to, take the muting off, whatever that is. And I noticed that the center tune meter is 2 or 3 needle positions to the right, which usually means out of alignment. Let's go to, I'm going to generate a laboratory signal in the middle of the band if I can find it. we're going to generate an identical stereo signal on 98.5 from a very nice, accurate generator. And let's see what we have. There we go. It's the same 2 dB channel differential, which again is not audible. All right, this is not becoming showing any fruition. All right, so what we're going to do is fill out some data on the estimate form as far as the normal estimate that we do. So first thing we're going to do is just check frequency response. And we'll keep doing it in the dark. I normally don't do it this way, but there's several ways of doing this. This is pretty effective and it's simple. You're just taking this generator and going through the different steps across the audible range from about, I think the bottom is maybe somewhere around 20 hertz and it goes up to 20K. But it's no difference. So this is flat across the audio spectrum. The other thing we want to do is take the dummy load off, drive this up to full power. There we go. So what we're going to do right now is put this in pause while I enter in some data. Now we're going to continue. All right, what we're going to do now is we did some measurements. We're going to do an internal visual inspection. Then take some tuner measurements. And of course the phone is ringing again. Pause. Okay, this is what happens when Carol's not in. I get to answer the phone. So we're going to do a visual inspection and we're going to do some tuner measurements. Whenever we take something apart, we label all the pieces so we know which goes to where. 1447. The inside looks pretty good, and there has been work done on this. The 2 large capacitors here, the original ones have been removed, and more modern replacements have been put in. Mechanically, pretty nice installation. I don't know what the values are supposed to be. These are labeled 15,000 mics at 50 volts, but that looks like pretty good work right there. And the top looks good. It looks like capacitors on the audio driver board have been replaced. I just did an 850 yesterday, so I'm pretty familiar with these, what they're supposed to look like. What hasn't been done is the heat conducting compound on the driver transistors has not been replaced. Guaranteed that's bone dry, as is the heat conducting compound on the, let me get that here. The output transistors is bone dry. That's essential. That The two metal surfaces and the insulator between are not the most efficient conductors of heat. If heat is not conducted away from the semiconductors, they heat up, and when they heat up, they cause more current. More current causes them to heat up more, which draws even more current. So we go into what's called thermal runaway, and they self-destruct. Heat conducting compound is an essential. Let's see what else we can find. Oh, I see that the original incandescent lamps have been replaced with LEDs. I like that. All right. I thought they looked a little different. The indicator lamps are still the same, but the panel lamps are LEDs. I like that. Anyway, let's get the bottom of this off and take a look at what's down here. I'm going to do some more measurements. So, oh. You know what? We can zoom out a little bit here. And the overview on this is pretty good. Whoever was in here replaced electrolytics on the regulated board, which is pretty much mandatory stuff to take a beating. Also has, looks like you put in new DC pass transistors, and there is some new heat sink compound on them. So that looks pretty good. Pretty good. All right, so that's about all I can visually see, and I see nothing objectionable visually. So we're going to put the item down and continue with some measurements. One of the things I want to do, and we're going to turn the light back off again so we can see the scope, is I'm going to tap on the speaker relay and see if that affects anything. All right, so let's go back to our scope and get the lights off so we can see it. And we're in auxiliary, and there's our signal. And let's just zero in, get a little closer so we can see any indifference. What I find fascinating is, we're okay. Yeah, no, we still have the same channel imbalance of a decibel or two, which again, in the real world is not audible. All right, so we're up at 0 dB. Let's tap on the speaker relay. No, it's rock solid. Well, Gary, your item is not exhibiting any intermittent problems showing up as channel indifference. Whoever did this work, pretty good. And I normally don't do this, but let's just take a look at DC offset and DC idle bias. Then we're going to go do some, I need some light to do this. Then we're going to do some tuner measurements. And I'm going to turn this off real quick while I'm doing this. I'm trying to find a piece of one of these emitter resistors that I can put my clip leads on, and it's the blind side. It's underneath, so I really can't see them. Had it going. That's not happening. That's not happening. Okay, I think I got it there. So what we're going to do is check DC offset. And usually a more accurate reading occurs when you let it run, but this is going to be close enough for government work. Just turn the item back on, and offset's good, 25 millivolts. Actually, no, the ground part of the meter was not good. Offset is higher than I want it to be. It's about 170. Can you see that? Yeah, it's the gray meter. It's this meter here. It's hard to see. It's jumping around, actually. It's down to about 100 now. But ideally, it should be zero. In the real world, it's never zero. But it's actually jumping around, which is not a good thing. I don't know if I can zoom in on that meter, but let's try it. No, not that meter. That meter. There we go. That meter. It's jumping all over the place. 126. Ideally, it should be zero. In the real world, it's never zero. But then we're going to do is take a look at the bias. Whoops. Yeah, we're going to turn it off. We don't make connections when power is applied. That's a rookie mistake. Geez, it's hard getting to these emitter resistors. You know what? That's the same point. Okay, let's take a look at bias. Yep, that's certainly acceptable. All right, so I don't like DC offset. Bias is okay. Let's go to the other channel. Do the same thing. And what I'm doing on the other channel that you can't see is I'm on the blind side of one of the emitter resistors trying to hook the lead for the meter. And of course, it's not happening. I'm going to cheat. Go to this one that I can actually see a little bit on the other side. Okay, there's our DC offset on the other side. Again, it should be ideally 0. The real world is going to vary. I usually don't like them up around 90 like this is. But I usually like to keep them 25 or less. But it's still working with 90, although it certainly is in textbook. And let's take a look at the bias. I'm just going to shut it off real quick because we don't want to make the rookie mistakes. And here's the bias on the right side. Pretty good. Okay. So now we're going to do some tuner measurements. I never do idle bias or offset in an estimate, but because someone has been in this, I want to make sure that this isn't going to blow up in front of us. Okay, so let's back this out. And we're going to do some tuner measurements here. Oh! So first thing we're going to do is go to AM, turn the machine on. Boy, those LED lights are something else, aren't they? Wow. I like them. All right. So here's AM, and we're kind of in a semi-industrial area here, so there's a lot of extraneous AM type noise. What we're going to do is do a rough check for sensitivity. My normal benchmarks, I'm coming in as good as they normally do, but there seems to be a lot of atmospheric noise today too, so we're going to say maybe the sensitivity is okay. We don't really make quantitative measurements on AM, but as far as sensitivity, but we are going to measure dial calibration, and so we're going to go to a number 10. Number 10 is at 600. Right on the money. I like it. And the other end is the high end, which is 1400. Very nice. Just going to pause this while I enter that data. Okay, now we're going to have some more fun. We're going to go do FM where we do actual good measurements. Number 1 is the center tuning meter is several needle widths to the right, which usually indicates an out of alignment condition. It can also indicate defective components, but 90% of the time it's alignment. And I'm going to make note of that in the estimate. So you may have a little inactivity here. The center to the Okay, that data has been entered. Now, let's go over in FM. And first thing we check on FM is dial calibration. And low end is 21. Low end, a little bit off, 90.2. We're going to do the high end, which is 106. Yeah, 106.2 also. Ooh, now let's take a look at sensitivity. Sensitivity, not something to write home about. Okay, hang on. We've got a little standing wave on the cable. Sensitivity is about 21, 2, 3. About 7.2 microvolts. This receiver can do better than that. All right. Now let's take a look at distortion. Wow. Nice. Actually, let's center tune it, see if it's still nice. Okay, distortion in... Let me see what the camera's showing here. Yeah, okay. Distortion in mono is about 0.13%. Off the top of my head, I don't recall if that's a good number for this receiver, but it is for most, I'll tell you that right now. It's certainly not anything that a human can hear. And let's take a look at stereo distortion. Yeah. Stereo is a little higher, and again, I'm off the top of my head, I don't know what the spec is for this. It's about 0.32. That may be a little high, but we'll take a look at the specs later. 0.32. And now we're going to do separation, stereo separation. Whoa, that is not good. What is that? Hang on. I must have something set wrong here. All right. No, that's not right. Okay. Stereo separation is pretty bad. That may be why. I'm going to show you. I'm show you the camera. Here we go. Let's go up here. Typical spec on this caliber of receiver, I expect the separation to be greater than 40 dB. Okay, and what we're going to see up here when we zoom in is pretty poor, which is why I keep looking at the switches and controls. I must have this set wrong. No, it's not in mono, it's in stereo. But I just went to mono. I'm sorry, I just went to both channels being transmitted. Okay, now I'm going to go to just the left, and we now have only a 5 and 3. We now only have a 8 decibel separation between channels. Again, should be greater than 40 decibels. Let's just generate a right only. Same thing. Let me make sure the camera's getting that. No, it's not. Hang on. There we go. Okay, let's do that again. We're generating just a right signal now. Let's just go back to the beginning. Here we are generating both a left and a right. Here we're going to generate just the left, which is the upper display, which means the right should be theoretically 0. In practice, should be greater than 40 dB. Right now it's 8 decibels, 8 dB. I can generate just a right signal, and we have the exact same result, only an 8 dB difference. That's not even close to being good. Not even close to being good. And again, I'm looking at the controls. I don't have it in mono. Let's go back to this. I don't have it in mono. No, we have a problem in multiplex. Okay, that's what we found. We actually found something wrong with this. Glaringly wrong anyways. 8 dB. All right, now the rest of the estimate is, I interpret these measurements and then we do a proposal. So as far as the actual bulwark of doing the estimate, that's what it looks like. That's what it takes to do an estimate. And we're going to email this up to Gary, our customer.